Okay, we're starting the next class of electricity chapter. Uh, we talked about the band theory last class, which is not given within this note. That's why I started with that, so that we do not miss out on that. The band theory is basically the idea that how much energy is required for multiple objects to become insulator or conductor or semiconductor. So we talked about those stuff. The lecture is already up, so you can look it up on YouTube as well if you want. Today we're going to start directly from this point and we'll go on forward this thing. So you know these parts already. These equations are from your O levels. So we'll start from the internal resistance. The key part for internal resistance is that ideally up to O levels, we have learned that any battery or cell was considered to be ideal. Ideal means the cell would only provide energy without any resistance. But the truth is, a cell cannot have zero resistance. I mean, you need to think. If you think that if I try to draw the basic process of a cell in a very simplified diagram, let's say this is a cell. I'm going to draw the circuit symbol for a cell. Let's say this is a cell, and let's say we have connected a bulb over here. And if we close the switch, let's say this is a closed switch, and this will cause current to flow in this direction and electron to flow in this direction. So this is the flow path of the electron. Now, you need to understand this thing. The cell does not create electron. All that it does, it uses its chemical energy to pump the electrons from this plate into this plate. The chemical reaction that happens within a cell will always pump the electrons. It's like a pump. Using the chemical energy, it will pump the electrons from this plate to this plate. So as a result, this one will become positively charged, this will become negatively charged. As long as the chemical energy is there, this will keep on happening after. And when the chemical energy gets depleted, the battery life is over. Now, you have to understand, for this to actually happen for a significant duration of time, these electrons, which are going to get absorbed on the positive plate, has to actually travel through the cell to reach out to over here. The cell will do this thing, but physically, think about it physically, the electrons will have to travel through this path. Electrons, as the electron will travel through this path within the cell, they will gain electrical energy. The chemical energy from within the cell will be delivered to the electrons as electrical energy, and from this position, they're gonna travel with their high energy state. They're gonna come up over here, lose their energy in the device. I have drawn a light bulb over here. So in this case, electrical energy will be converted into simultaneously light and heat energy. So L plus H. And then the de-energized electrons will simply flow through this rest of the circuit wire and eventually reach up to this point over here. And this process can happen indefinitely. It is very much possible that one single electron can travel through the circuit like hundreds or thousands number of times, depending upon how much energy did we pack in the cell to begin with. So what I want you to understand that it is practically not logical that electrons would be able to pass through this cell unobstructed, because a cell essentially has a cathode, it has an anode, it has an electrolytic fluid, which basically is the reservoir of the chemical energy. The electrons have to physically be able to pass through these gaps, through these objects, and that basically introduces some resistance. Now, typically cells are designed in such a way so that the internal resistance of a battery or cell is as low as possible. It can never be made into zero. That is physically impossible to achieve, but they are designed in such a way so that it has the least amount of resistance possible. And this is also why joining multiple cells, I mean too many cells in series, can lead to a very large amount of heating effect in the battery. So it's not recommended. And this is also why DC circuits cannot work in high voltages. DC circuits always work in a low voltage. For example, if you have an IPS in your house, if the IPS runs on a one lead acid battery, the supply voltage of the battery is only 12 volt. If it's a bigger IPS, if it has two batteries, two lead acid battery, rechargeable battery, actually those rectangular box kind of batteries with metal heads on the top, then the sub voltage is actually 24 volt. DC circuits cannot work with higher voltages, because the only way you could achieve high voltage for DC circuit is by connecting multiple cells in series. And the more of these cells you're going to connect in series, bigger amount of resistance you're going to accumulate up, because in the law of series resistance, it just gets added up. So that's actually not a very useful idea, because the more resistance you have to actually overcome through the source itself, the more loss you are making before you actually can deliver this thing to the actual output circuit. So this is the basic idea, theoretical idea for why internal resistance does exist. You just have to know why it exists. You don't have to remember all of this battery construction, everything. I talked about this stuff to give you a concept that why this thing exists. I mean, why this was not the reason it was not introduced in your O levels, because that was a very primary level. We are basically skimming the surface of the electricity part. So you are basically given a very simple stuffs and formula and mathematical orders. Now we're getting into a bit deeper situation. So that's why you're introducing the idea of internal resistance. And and for the internal resistance to work, let me use this exact circuit over here, and I'm going to use red for the upcoming writing. I'm going to choose a thicker line. Let's say, let me draw a new circuit. Let's say we have a battery of 6 cell maybe. Okay. Currently, this battery is not connected to any circuit. And once again, let's say we are going to introduce an ideal voltmeter. Now I'm using the term ideal. This essentially means what? I mean, in
Zero
physics,
resistance.
no, in
It has
physics,
no resistance.
it has what?
Infinite.
No. It's a voltmeter. It has no resistance.
Infinite
It has
resistance.
infinite resistance. Ammeters are supposed to have zero resistance.
Okay, sir.
বুঝছো কেন? Ammeters are supposed to be in series. Voltmeters are supposed to be in parallel. So voltmeters
বুঝেছি,
should have.
sir.
Okay. In physics, the word ideal means, first of all, I mean, the way I understand it, the word ideal means it does not exist. And also, it is a highly simplified version of the true thing, because we are learning and slowly we're going to add up more and more complexity to this thing to make it as close to real, and we are going to slowly learn those processes. So let's say this is a regular battery and this is an ideal voltmeter, which means let's consider this voltmeter has infinite resistance. Unless I specify otherwise, we're going to consider all the ammeters and voltmeters that we're going to discuss for the upcoming part of the lecture as ideal components. So I'm not going to use the term ideal all the times, but unless I specify otherwise, they are going to be referred as ideal voltmeters or ideal ammeters. If we connect, let's say this battery on its body, it has labeled, let's say 12 volt. If we connect a voltmeter across the two ends of this battery, this voltmeter will give us a perfect reading of 12 volt. You do understand? Yeah, that's of course this is going to happen. Now let's say we are going to connect a light bulb over here with a switch. I'm going to turn on off this switch. So that's why to begin with, I'm actually just starting the circuit with an on switch, open switch, or the circuit is currently off. The bulb is not glowing. There is no current flow in any part of the circuit, so it's okay. And just to be curious, let's say we have connected another voltmeter across the bulb. For easy understanding, let's say this is voltmeter 1. Let's say this is voltmeter 2. Now try to understand this thing. Let's say the actual resistance of this bulb is capital R and the internal resistance of this battery is small r. The moment we're going to close the switch, current is going to start flow through this circuit. EMF of this battery is of a battery or of a source is usually represented by the symbol capital E. So I'm using E as over here. So if I write the equation, the total resistance of this circuit is the combined series circuit resistance, which is this rectangle. So the current of this circuit, if we have an ammeter over here, the reading of this ammeter in series, this should be E divided by R plus R, because this is the combined resistance of the circuit. It is বুঝাচ্ছে?
Yes, sir.
Now think about, we are going to have some voltage difference happening across this component, and we're going to have some voltage difference happening across this resistance. If I write it more precisely, let's say the voltage drop that happens across the load resistance, let's say this is what we call a load resistance. Load resistance basically means the resistance which where we actually want to spend the electricity. That's what we call a load. Let's the voltage across the load resistance, or I'm going to write V2. This would be I into R, and the V1 should be either 12 or it should be something else. Now my question to you kids, when the switch is closed, what should be the V1 reading and what should be the V2 reading? I want you to respond in terms of equal to 12, more than 12, less than 12. I'll
Also
say,
less than 12.
I'll say the question again. The moment we close the switch, the moment we close the switch, what are we expecting to be the reading of voltmeter 1 and voltmeter 2? I want you to choose from three options: equal to 12, less than 12, or more than 12. Which one do you think is going to happen?
Less than 12?
Both of them?
No, only equal.
All right. Let me tell you what is going to actually happen. If I actually try to assign some numbers, it will be easier for you to understand and remember this thing. Let's say we assign some numbers. Let's say this load resistance over here is, let's say, 10 ohm, and the internal resistance of the battery is, let's say, 2 ohm. I'm conveniently choosing these numbers so that my current will become 1 ampere. So in this case, I'm going to write 12 divided by 10 plus 2 gives me 1 ampere. So the voltmeter reading 2 should be how much? 1 into 10. How much are you going to get? 10 volts. And what should be the reading of voltmeter 1? Now, this is the part that you really need to apply some of your electrical understanding. What should be the reading of voltmeter 1? I believe you kids are thinking. I'm audible, right?
Yes, sir.
Yes, sir.
Yes, sir.
Before I tell you the answer, I'd like to take your attention to one part of this circuit. Have a look. Electrically, these 2 points are same points. Do you agree on this? There is no resistance in between.
Yes,
So
sir.
they are electrically equivalent points. Similarly, electrically, these 2 points are also equivalent to each other. These 2 points when the switch is closed. Which means having a voltmeter connected across these 2 points and having a voltmeter connected across these 2 points pretty much mean the same thing. Leads us to the understanding when the switch is closed, the voltmeter 1 reading should also be 10 volt. Now you might wonder, where did this other 2 volt go? This 2 volt is being spent within the battery to push the electrons through the battery itself. And this is the loss that we're going to talk about after a while. So in this case, the lost voltage, which is usually represented by a small v, is the current into the internal resistance, which is going to be given by 1 ampere into 2, which is 2 volt. Now we have the full picture.
Sir, internal resistance means resistance of the battery, right?
Yes, or source. If you have a DC source which is not a battery, I mean it means it means the resistance of the source. To make an example, a DC source can also come from a solar panel. A solar panel can also work as a DC source, but you cannot actually convert all the light energy absorbed in the solar panel as an electrical output. Some energy has to be spent to run those electrons within that solar panel. That resistance is what we call internal resistance of the solar panel, and the amount of voltage you're going to lose to run those electrons within the source itself is what we call the loss voltage. So if I put it in this manner, that we call this one terminal voltage. This is the new term, and this is a very specific term. You cannot use other variables. So this is a fixed term, new term. This is what we call terminal voltage, and this is one of the questions that I got asked when I was giving my interview in Oxford back in 2010, and I forgot this term and I could not answer this, and eventually I did not get picked to do the job in Oxford. Anyway, so this is so since then I never forget this term. So this is this voltage that happens across the load of a circuit is what we call the terminal voltage, and the voltage that gets lost within the battery is what we call lost voltage. So this is actually pretty simple. Lost voltage is lost voltage, and the other one is terminal voltage. For this circuit, the terminal voltage is going to be 10 volts and the lost voltage is going to be 2 volt. So to summarize the whole thing one more time, when the switch is open, I'm going to go through this a bit slower. So I want you kids to hear me out, and if you have any question, ask me. When the switch is open, voltmeter 1 reads 12 volt and voltmeter 2 reads 0 volt. Can we all agree on that?
Yes, sir.
Everyone, get to the same page. When the switch
Yes,
is
sir.
open, Voltmeter 1 reads full 12 volt and voltmeter 2 reads 0 volt. So if I just write switch open, V1 equals to 12 volt, 12, I mean need to be 12, and V2 equals to 0 volt. When the switch is closed, both V1 is 10 volt and V2 is also 10 volt. And 2 volt cannot be seen anywhere because you cannot actually measure 2 volt. The only way you can trace out the 2 volt is by mathematical calculation. I mean, loss voltage can be only, loss voltage is a thing that you cannot measure directly. You can have to measure it indirectly, opposite word, indirectly. So you know that the initial reading was 12, you get the current reading is 10, which essentially means if you do the subtraction of these two numbers, you will get the loss voltage. So that's the basic idea for the loss voltage for the voltage scenario. I'm going to use this small space that I have left over here to show you the power consumption, but I'm going to write a bit smaller, and I will realign myself so that I don't write to the sky anymore.
স্যার
Yes.
সুইচটা ওপেন থাকে তখন হচ্ছে তো মানে সার্কিটে কোনো কারেন্ট থাকে না, তাহলে ভোল্টমিটার রিডিং দেয় কেন?
Ideal voltmeters don't need current for the reading, but practical voltmeters do pull a little bit of current. I mean, ideal voltmeters can work with zero current. Like I said, ideal, which means non-existent and super simplified. Practical voltmeters draw negligible current from the source to give the reading. Make sense?
Yes.
Okay.
So
As-
স্যার
বলো।
সুইচ ওপেন থাকলে কি প্র্যাকটিক্যাল ভোল্টমিটার 0 রিডিং দিবে?
No, hold up. Switch open থাকলে practical voltmeter 0 reading দিবে. Yes. No. Sorry. Switch open থাকলে V1 no 0 reading, V1 দিবে 12 আর V2 দিবে হচ্ছে 0. আচ্ছা, hold up.
V1 12 কেন দিবে?
এক minute. What will be the scenario if we attach practical voltmeters in different places? I'm going to cover it in a separate part of that discussion. I don't want to bring it multiple variables at the same time. For the time being, let's constrict our discussion within the ideal components, and only the battery has internal resistance. I'm going to discuss the implication of practical ammeters and voltmeters just a bit later. একটু ধৈর্য ধরো, ঠিক আছে? Okay. So I'm going to write the equation of power over here. The total output, the total power drained from the source, so power of the source, how much power is the source losing? The power of the source is I square into R plus R. This is the total resistance of the circuit. This is the current flowing through the circuit. So this is the total power that is coming out of the source. Among this power, the useful power, or we can also write power of the, I shouldn't write comma. I can either write useful power, or sometimes this is also written as power of the load. The load power is only I square R. And the lost power or wasted energy, wasted power is I square small r. এই পার্টটা কি বুঝা যাচ্ছে?
Yes sir.
আচ্ছা, if you do understand this properly, then the next equation would make sense. So the efficiency of this circuit would be power useful divided by power total. I could write source, but just to make yourself acquainted with multiple variable words, I'm using the total. So I can replace those equations over here. I square into R divided by I square into R plus R. And if you cross out these two I squares, you basically get the resistance on the top and R plus R at the bottom, which basically means that you can never make an actual circuit, electrical circuit, no matter how good, 100% efficient. You will always have some loss. But magic happens when we optimize something to a very high value. The better optimization or better design you can make, you can reduce those losses. Basically, in the current industry, current world, on a large scale, Tesla, the electrical car company, they are doing it better than everyone else. They are battery assembly or their battery pack assembly is such that they are capable to produce the least amount of heat, and they are also able to remove that heat more efficiently than any other car designers. So that's why they are on the top. Even though all of their researches are open source, but no, the reason no one can actually come to this part, because this is the part that this installation part, not the actual technology, this installation part is something that they have kept as proprietary. Okay, any questions so far? এ পর্যন্ত বুঝা গেছে সবার?
Sir, power useful divided by power total power এর সাথে 100 কখন যেন মাল্টিপ্লাই করি?
100 আমরা যে কোনো জায়গাতে মাল্টিপ্লাই করতে পারি। তুমি যদি if you want to express the efficiency as a fraction মানে let's say 0.76, that's also expression of efficiency. Or if you want to express this as a percentage, you simply multiply by 100%, which basically means 1, then you get 76%. Multiplying by 100% is an optional thing. If you want to express it as percentage, then you multiply by 100%, because the total value, numerical value of 100% is basically 1. It's about
Yes.
it's about in what form do we want to express that information? Do we want to express it as a number, or do we want to express it as a percentage? That's basically the difference. All there is. আচ্ছা, এটুকু পর্যন্ত আমরা বুঝলাম। এরপর আমরা একটা ভেজালা জিনিস দেখবো, যে ভেজালা জিনিসের ডেসক্রিপশনটুকু তোমাদের সিলেবাসে আছে, রিজনটুকু তোমাদের সিলেবাসে নাই। ইটস নট অ্যাকচুয়ালি ভেজালা জিনিস, ইটস নট অ্যাকচুয়ালি কমপ্লিকেটেড, বাট there is a reason. I mean, some part of this upcoming part is actually simple. If you want to just take the description, like I'm gonna, for the next part, for a small segment, I'm gonna tell you and discuss the what is the information. I'm not going to discuss why that information is logical, which brings us to this thing. If you plot a graph of load versus the load resistance, if you plot a graph of these two variables, let's say you have a fixed source which has a fixed EMF of E. The way we actually represent, let me show you in the actual format. The way we actually represent our battery with internal resistance is that we draw a dotted line around the battery, and inside the battery we represent it by a small resistor like this within the small dotted rectangle. So, and this is usually labeled as smaller, and the EMF is usually written anywhere outside. It could be written on the top, bottom, doesn't matter. So this is a battery of EMF E and internal resistance R. If we connect this thing to let's say variable resistor and have a circuit, obviously we're going to need the ammeter, and we're going to also need the terminal voltage measurement. So we're going to need those things. And let's say if you slowly start to change the value of the variable resistor and take pair values of A and V, product of these two readings will give you the actual output power, because this is the current, this is the resistance voltage, so power equals to V into I, so that works. And you will also know the resistance of this resistor because you're going to choose that number, that how much resistance are you putting, so you'll also know this thing. So practically we can this power over here basically give you the load power, so power of the load. So because this is the output voltage, or this is the terminal voltage into current gives you the load power. EMF, interesting information, that power, this is the load power, whereas if you want to get the battery power, or if I can write the total power, or if I want to write the source power means how much power is given out from the source, that can be given by the EMF into I. You have to understand these two numbers will never be equal. Which number is going to be bigger? Can somebody tell me?
Source.
Second one.
The right one or the left one?
Right one.
Right one.
The right one.
The right one will always be bigger, somewhat bigger. Beautiful. So we can actually get this number. We get this number by some calculation, and we will also know the value of the resistance. And if we plot a graph of these two variables, that graph gives us a shape like this. Now, why does the graph has a shape like this? This part of the lecture, this part of the information is not included in your AS syllabus, because this actually has to be drawn by a lot of replacement over here. I don't want to show you the replacement, but if any of you interested, if you stick up to the end of the class and ask me to show you, I'll actually Google the whole thing and I'll show you why this was not included. But I don't want to discuss it on the class because this is not in your syllabus. But I can show you, take you to the necessary understanding for why it is like that. So if we eventually do this experiment, we're going to come up with a graph like this. What happens is that the point where we get the peak load power is the point where the load resistance is exactly equal to the internal resistance. Now, once again, why does this happen? I'm not discussing. I'm only telling you that this happens. So this is the type of a circuit that can help us to draw this graph. You have to know the structure of the circuit. It's a pretty simple circuit. You can see it. You understand how the circuit works. And you also have to know multiple property of this graph, that the graph has a shape like this. There is a maximum power over here. The maximum power is only achievable for a setup where the internal resistance of the source and the load resistance, they're exactly equal to each other. এটুকু পর্যন্ত তোমাদের সিলেবাসে আছে, এটুকু পর্যন্ত জানলেই হবে।
এটা
আর
কিভাবে ইকুয়াল হয় সেটা তো জানতে হবে না, তাই না
না না
স্যার?
না 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 না। আর আরেকটা জিনিস হচ্ছে যে the additional part to this thing, which is on the shaded part of the syllabus, which is that, I mean, here this is a graph of capital R, which means here the load resistance is 0. So it slowly we're increasing the load resistance. At this point, the load resistance became equal to the internal resistance, and then the load resistance got bigger than the internal resistance, which means for this much segment, this is true. And for this much segment, this is true. Now, if these are true, because they are both run on the same circuit, I can obviously write, if I multiply the I square on both sides, I have a reason to do that. I square R should be bigger than I square R. And for this region, I square R should be less than I square R. Try to think about it and tell me which side of this graph is energy efficient. Left or right? If you want to run an efficient system where your loss is less and output is more, which one would you prefer? Would you prefer this segment or this segment?
স্যার রাইট সাইডেরটা।
That's the correct response. But do all of you agree on this?
Yes, sir.
Yes, sir.
Obviously. So typically circuits are designed in such a way that this should be as small as possible. You can see over here, this rise is actually pretty sharp, but the fall is not that sharp. So it means that there actually lies a pretty long graph. It can become actually a pretty long graph. We want to achieve a point, we want to achieve a sweet spot somewhere on this decreasing graph, such that our output power or the load power is also quite high, so that it is useful for us. And also our efficiency, our wasted energy is also quite small, so that we don't lose too much heat. Because losing too much heat is obviously a problem. You are going to run out of the battery pretty fast. But if you, that's one side of the problem. The other side of the problem is that if you produce too much heat within your battery, you need to actually install cooling systems to your battery. Because if your batteries get warmer over the usage, that heat energy will introduce more resistance within the conductor materials. So you are simply gonna keep on losing more and more energy. So it's basically like a vicious circle. So we don't want that. So what type of equipment are you running and what is be your optimum value? That actually depends upon the design, and different application can choose to do different things. For example, if you ask me, if you could think for an electric car which is aimed to run for a pretty long distance, they should preferably choose a point as far right as possible, so the efficiency is pretty high. However, if you think for a handheld drill, battery powered drill machine, or a battery powered screwdriver, then you can also choose to be somewhere over here, because those handheld drill machines, you're not going to run it continuously. You're going to make a drill, put down your drill machine, do the necessary installation over here, and then you're going to pick up the drill and do another drill over here. So there are intermittent gaps over here. Within that gap, the battery can cool down. So in that case, you can choose to have a higher load power, so that you can actually have a stronger torque on your motor. So it is an application specific choice. Does it make sense?
Yes, sir.
ওকে, আমি শেডেড বাউন্ডারির ভিতরে অনেক কিছু বললাম যেগুলো আমার আমার মানে আমার আমি জানি জানি বলে বললাম, বাট সবকিছু যে তোমাদের লাগবে এরকম না, যতটুকু পারো ততটুকু মনে রাখো, বিকজ শেডেড বাউন্ডারি ইজ শেডেড বাউন্ডারি, সো there is no hard and fast rule that what is actually needed and what is not. So এটুকু গেল হচ্ছে আমাদের ইন্টারনাল রেজিস্ট্যান্সের কিচ্ছা কাহিনী, এখানে শেষ। The next thing that we have in our electricity, this is actually a new part for our AS syllabus, that's why we discuss this thing in elaborate version. The next thing that we have for our AS syllabus is null method. Comparing the EMFs of unknown cells, why is that important? Okay, never mind, I think this was a invalid heading, disregard this heading, these things are continuous. There is a thing called null method. Now you might wonder what? Yeah, it is a method of doing some measurement where we would try and achieve something to become zero. Making something zero will enable us to measure something else. Now for some of you it might look weird, but let me tell you this thing. Do you guys know beam balance?
Yes, sir.
Daripalla, basic Daripalla, beam balance. Now a beam balance gives us a proper reading only when the beam is horizontal, which means when the height difference between the two sides of the beam balance is zero, that is exactly when you have the appropriate mass measurement or weight measurement on your beam balance. Am I correct?
Yes, sir.
So to make a beam balance work, you have to first make the height difference between the two sides of the beam zero. Once you make sure of that, something else can be measured. The null method is pretty much like that, but obviously it's electrical circuit, so the working is different, but the theme is that we're going to make something zero and use that privilege to measure something else. So let me just show you how this works, and it's pretty interesting. Here's the thing. Now comes to the idea of practical voltmeters. Practical voltmeters, I mean ideal voltmeters, has a resistance that is infinite. My handwriting as poor, more poor than ever, infinite. Whereas practical voltmeters, I can write real voltmeters, they have negligible resistance. I did not use equals to, I have about. They are designed to have, sorry, I'm bullixy. They have pretty close to infinite resistance, which means, I mean, achieving infinite resistance is practically impossible, because I always say, and it's true, given enough voltage, anything can be made into a conductor. Given enough voltage, anything can be made into a conductor. So real voltmeters have close to infinite resistance, or in other words, we can say the voltmeter resistance of a circuit should be significantly larger, at least couple of orders of tens magnitude. For example, let's say 10 to the power 4 or 10 to the power 5 times bigger, orders of tens power bigger compared to the biggest resistance available within the circuit. Whenever we can achieve this thing, then we can consider that thing to be working properly for our purpose, and we can move on with the error. So that's how the practical scenario works. It doesn't have infinite resistance. Now here's the catch. Let's say we have an EMF over here. We just made, before I say we just made, let's say this, there is a battery that you have bought, and on the body of the battery it is written 12 volt, which means the company is aiming that they're saying that the EMF of this battery is 12 volt. Now let's say you want to check electrically whether this EMF is actually 12 volt or not. How would you check that? Well, you might think, well, I can connect a voltmeter. Okay, let's say you connect a voltmeter. Now we're talking about real voltmeters. Let's say this is not an ideal voltmeter because they're not available. You're practically trying to measure the EMF of a given battery. You can never get 12 volt over here because the resistance of this voltmeter is not actually infinite. It has some really high value, but it is not infinite, which means the current is gonna be 12 divided by the resistance of the voltmeter plus the internal resistance. This number can be very large. This number can be very small. But when you are gonna get this fraction value, You are never gonna get perfectly zero. You might get really small number, but are you gonna get zero? Think about it. It's a fraction. 12 divided by some number. That number might be very large, but the fraction, the division will never give you absolutely zero. Do you agree on this?
Yes, sir.
Okay, which means for if you connect a practical or real voltmeter across a source, there will always be some current. No matter how small, there will be some negligible current flowing. The moment there is a bit of a current flowing, this battery will do its loss voltage thing. This will come into existence, and then the voltmeter is going to read E equals to, sorry, the voltmeter is going to read what is left. So voltmeter is going to read E minus IR. That will be the reading of the voltmeter. It cannot read the full E because the battery is simply not going to give an output of V of 12 volt, because it will have to spend some energy, it will have to spend some voltage to overcome its own resistance, because now current is flowing. So you cannot ever get this reading to be exactly 12 volt. That is not going to happen. You're going to get something more or something less. What are you going to get? This voltmeter reading should be what?
Something less than 12.
Exactly. This voltmeter is going to be something less. If your equipments are really good, maybe you might as well get, let's say, 11.99999. Maybe after a lot of 9 there comes something else than 9. That's possible, but you should never get 12. Why am I telling you this? I'm trying to instill the idea within your head, within your understanding, that using a direct method like this, we can never measure the actual EMF of a source. It is not going to work. So how can we measure the EMF of a cell truly without internal resistance in our path, or discarding the problem related to the internal resistance? How could we possibly measure the EMF, true EMF, whole EMF of a cell or of a DC source? Let's say you just made a biological battery using some lemons and one copper rod and one iron rod. You want to measure the exact EMF of that biological cell, or lemon cell. Let's name it lemon cell. How would you do that? That is the part of the lecture which is going to happen in the next part. Now let's have a look how this works. Do all of you remember the basic structure of a potential divider? Do you guys remember how a potential divider works, people?
No, sir.
Okay, I'll help you remember. Just a second.
Mhm.
Sorry, I went out to get some water. So let me help you to remember the potential divider circuit. Potential divider circuits can show up in a lot of different orientation, but the core truth or the content of the potential divider circuit is basically very simple. Have a look. The idea of a potential divider circuit looks like this. If you have a battery of large enough supply, let's say a battery of source voltage V, and if you want to take a fraction of this V out of this battery, how can you get that? One logical way is that we can use a variable resistor that has a sliding contact, or a jockey. A sliding contact is called a jockey on it. So let's say we are going to connect this source with a long variable resistor, and we're going to have slider over here. The slider is like that. This slider can move up and down while keeping contact with the resistance wire. So this resistor is the circuit symbol, but in the actual rheostat, in an actual rheostat, I should show you the figure so that you can actually visualize how it works. Just a second. The typical rheostat that we use in our laboratories look like this. This is a very high definition picture, 2000 by 2000. What if I copy this image and try to take it on a new MS Paint? All right. So let me show you what is happening. These wires that you see that is wound around this thing. Inside this, these wires are wound around a ceramic cylinder, which you cannot see over here because wires are covering that part. And these wires are insulated with each other. So they have a thin layer of insulation around them. So even though they are wrapped around and they are touching each other from side to side, there is no electrical connection between one wire to the other. So they are electrically insulated from each other. Here we have a look. Here we have a clamp kind of connector over here, and these, and there are actually two. One is over here, one on the back side, which you can slightly see over here. So these two actually clamp onto this coil of wire from two sides. And if we move this thing on this rectangular shaft, they can move around. And as they move around, these contact points actually remove some part of that insulation and can make electrical contact. If you wonder what, this is how the electrical conduction happen. Any rheostat comes with three ends. This is one, and this is the other one. The resistance between these two wire is the full resistance of this wire. So connecting, if we connect a certain circuit between these 2 points, we cannot get variable resistance because the resistance between these 2 points is a fixed resistance. How do we get a variable resistance? Let's say we're going to connect. Okay. Let's say we're going to connect. Let me use a thicker line maybe. We're going to connect one wire from this junction and take out and connect a bulb with a battery, large enough battery, and let's say we're going to connect it over here. Now try to understand the pathway of the current. The current should go through the bulb, come over to this junction. It has to travel through this metal shaft. You can see these are rubber gaskets. These orange things are rubber gaskets. So which means the current is not touching this structural metal body. Current is this is going to be connected over at a metal head over here, and that current is going to travel through this metallic shaft. And because within this contact they are connected to the contact, so they're going to flow through either this part or through that part. Ultimately, they're going to touch one specific length or one specific location on this coil of wire. And they cannot travel laterally because, like I said, they are like, these wires are very much like the way our fingers are aligned. Even if you touch all of your fingers side by side, your bones are not touching, your skins are. Do you get my point?
Yes, sir.
Okay, sir. So the current then have to travel through this entire coil, and eventually it is gonna come out of this right side, and then it's gonna come out through here and over here. So now in this circuit, the actual effective resistance that we're using is this part of the rheostat. This is the part that is actually introducing the resistance over here, which essentially means that if we slide this rectangular thing, which is actually what we call the jockey, this sliding contact is what we call the jockey, this device is what we call the jockey. If we slide the jockey towards this, then the contact is going to happen more on the left, and there'll be a bigger resistance wire that the current has to pass through. This will make the effective resistance of the circuit bigger, and the bulb will dim out because current will become less. And vice versa, if you move it to the right, then the current has to pass through a smaller length of the resistance wire. As a result, current will be larger and the bulb will glow brighter. That is basically how it works. Does it make sense?
স্যার এই জিনিসটা কি আরেকবার বলতে পারবেন?
Sure. কোন জায়গা থেকে বুঝো নাই বলো?
স্যার এখন যে বললেন যে ওই যে বেশি রেজিস্ট্যান্স ফর্ম করবে কম রেজিস্ট্যান্স ফর্ম করবে পার্টটা
Acha. Let's say let's say at a certain scenario the jockey is exactly over here. Now the effective part of the resistance that the rheostat is introducing belong to this part. This part. The current has to travel through this coil in round pattern and eventually it will come out through here. So whatever the length of wire you have over here, that is the amount of resistance of the circuit along with the bulb resistance. So you have some current. If you slide this jockey to the left, so I can try to do this. Let's say, can I make it transparent? Beautiful. I feel awesome. I can now say. No, man, sorry, my bad. So if we slide this thing a bit to the left, I hope it works. There is a glitch in the matrix. Anyway, if we move this slider a bit to the left, then the current has to pass through a longer length of wire. এই পার্টটা কি বুঝতেছো?
Yes, sir.
So the effective resistance of the circuit will increase. So the brightness of the bulb will
Decrease.
and vice versa. আমি বুঝে গেছে ক্লিয়ারলি?
Yes, sir. কিন্তু স্যার এটা এই জকিটাকে যদি আমরা লেফটে টুয়ার্ডস লেফটে স্লাইড করি তাহলে তো এটার মানে ওই যে লেফট সাইডের যেটার সাথে কানেক্টেড ওইখানে তো মানে হ্যাঁ এই বিটুইন এই দুইটার জিনিসের মধ্যে প্যাথটা তো ছোট হয়ে যায় তাই না?
Oh, beautiful
তাহলে
question. Beautiful question. These aluminum shaft is usually made from aluminum, or if it's made up of iron, it's galvanized. This shaft has such a large cross-sectional area that we can practically consider the resistance of this entire rod to be zero, practically. Compared to the resistance that we have within the wire, the resistance of this shaft is zero. Or you can think that electrons can travel from here through this shaft up to the contact point unobstructed, virtually unobstructed.
আচ্ছা স্যার।
বুঝা গেছে? So
Yes, sir.
এই সেটআপের জন্য আমি এই সেটআপের জন্য ছিল হচ্ছে if you move it to the right, current will decrease and vice versa. What if we did not connect this variable resistor or rheostat in this position, rather we connected that thing to the on the left position? What would have happened then? Think about it. If we cannot, let me use red. If we connect the wire right here, now try to visualize the path of the current. The current comes out, goes in here, goes through here, reaches over here. To complete the circuit, in which direction should the current go? Left or right?
Left.
It has to go to the left. So as the current goes to the left, it has to go, it's going to go through here and come out through here. So now the effective resistance will be the left segment, which means in this case, for this kind of connection, moving to the left will move to the left will reduce the resistance and current will what? Moving to the left will reduce and আমি এটা ভুল লিখছিলাম। I meant to write brightness. আচ্ছা আমি এটা আবার কারেক্ট করতেছি। আগে এটা লিখে নেই। When the jockey would be moved to the left, there would be let me write all the variables. Make it stupid. My bad. So for this scenario, when the jockey is moved to the left, resistance of the circuit will decrease, current will increase, brightness will increase as well. For this scenario. And as for the first scenario that we were discussing, moving to the right would give us those things. So where you connect actually matters. You have to just simply judge that which part of this entire coil of resistance wire is actually a part of your circuit. In this connection part, This is the actual part that is working on the left side of the siding contact. If you connect it over here, this is the active part. The remaining part is just useless. There is not a part of the circuit because current cannot go out anywhere from this point. So current is simply not going to travel through this point. Simple. Did I make sense so far?
Yes, sir.
সবাই
স্যার
everyone
আরেকটা
হ্যাঁ, বলো
কোয়েশ্চেন ছিল
বলো
স্যার ওই যে বললেন না যে ওয়্যারস গুলোর মাঝখানে যে ইনসুলেশনটা থাকে ওটা ড্যামেজ হয়ে যায় ওটা কেমনে হয় আরেকবার একটু বলবেন
এটা হচ্ছে মানে জিনিসটা কি আমরা বলি লেটস সে if you, I mean don't make a full fist but just try to if you keep your fingers touching all the other fingers touching. That's the typical scenario for this whole thing. Now think about it. Your bones are the metallic wires and the skin and the flesh that you have around your fingers, they are the insulation. Now let's say I'm going to keep my fingers in this very position just for the sake of discussion, and if I now rub off the skin of these fingers while touching each other from the top surface by rubbing a file onto my fingers, I can expose the metallic part on that location, right?
ইয়েস স্যার
And can actually make a contact with another bone maybe. So that's precisely how it works. This
আচ্ছা স্যার
বুঝছো?
ইয়েস স্যার
Beautiful.
থ্যাংক ইউ
No problem. ফুলমান এই জিনিসটার পারপাস বুঝে গেছে কি সবার? কার কোনো কোশ্চেন? Anyone else?
ঠিক আছে
Acha. Since there is no response, I'll assume you don't have any question, at least for the time. If you have questions later, ask me later. No problem. I'll answer your questions. No big deal. So if we go back to our original figure, so the way a potential liberator works, this is the variable resistance, this is the sliding contact, and if we take out two connection points over here, and uh, usually a flexible wire or a wire that can be actually be placed in different places is usually shown in a circuit by a curved line like that. So if you have a curved line like this, it means that this wire have enough length to be connected anywhere. Now, if we connect two voltmeters over here, let's say this is our voltmeter 1, this is actually the connection point, and let's say this is our voltmeter 2. The value of the voltmeter 1 and voltmeter 2 will actually depend where this jockey is placed. The location of this jockey practically divides this entire long resistance wire into two parts. Let's say, because we have named this upper part as voltmeter 1, let's say this length of the wire is now working as R1, and this length of the wire is now working as R2. So the current in the circuit is going to be what? V divided by R1 plus R2. So the voltmeter 1 reading or the voltage across the top part is going to be what? I into R1. So I can write V divided by R1 plus R2 multiplied by R1 equals to, so just because I want to keep the ratio resistance in a single ratio, I'm going to take this R1 over here and putting the V on the outside. So the equation simply becomes R1 divided by R1 plus R2. I'm putting this whole thing in a bracket just to look good into V. So this is the fraction of the voltage of the whole source, big source, you're going to get on the top side. In the same set of equation, the V2 will be R2 divided by R1 plus R2 into V. এই পার্টটা কি লজিক্যালি বুঝা যাচ্ছে? Are you clear with this part? I hope it is okay. Now, additional to this, one thing is important, that what if we have some other resistance in the circuit? Let's say, what if we had another resistance? I'm drawing this with blue. What if we had another resistance over here? Let's say that resistance was named as, let's say, R3, which is not part of the variable resistor, but there is a fixed resistance over here, R3. No big deal. That simply gets added at the bottom. I mean, the way this fraction works is that you place the resistance of the between the two terminal points. So over here, this is one terminal, or basically this is one terminal, and this is the other terminal. So this part of the resistance goes on the numerator, and the entire resistance of the circuit goes on the denominator. So I'm going to write R relevant. This is just some equational format that I came up with to make sense with kids. You should never write this in your actual answers. I can write the R relevant divided by R total. To get this ratio and multiply it by the source voltage, you basically get the voltage output of the relevant part. এটাই হচ্ছে এই ইকুয়েশনটাই হচ্ছে পটেনশিয়াল ডিভাইডারের বেসিক ওয়ার্কিং প্রিন্সিপল। Does it make sense so far? আমি এখানে 2 লিখছি বলে এটা 3 হবে। বুঝা গেছে কি এটা?
স্যার এখানে V তো V1 plus V2 তাই না?
Yeah, no, without the R3, yes.
With R3 কি হবে কি?
If there is an R3, then V equals to V1 plus V2 plus V3. In this case, we don't have any voltmeter across R3, but that doesn't mean it doesn't cause a voltage drop. It does cause a voltage drop, but we did not connect a voltmeter over here, so we are not going to measure that. But that does exist. The R3 will also produce its own voltage drop.
Okay, sir.
Sure. এই সেম সার্কিটটাকে আমরা চাইলে হরাইজন্টাল করে রাখতে পারি। এখন আমি তোমাদেরকে একটা হরাইজন্টাল সার্কিট দেখাচ্ছি। Let's say we have a big enough battery with a little bit of internal resistance over here. Let's say we're going to name this battery as E1. Whenever I say E1, you do understand that there is going to be another, at least one more battery, which will be named in that order. So let's say we are naming an EMF as E1, and this internal resistance, let's say we name it as R1. I should use black for the timing. Okay, let me use black. Switch to black. We're going to connect this thing with a variable resistor. I'm actually first constructing the whole thing, and then I'm going to describe the purpose of each of this component one by one. So you might have questions in the middle, but my request is that let me finish, then I'll take all of your answers. So hear me out first, then I'll tell you. But if there is such a case that you missed out some of my voice, or there was a lag, pause me immediately. Just শুনতে পাইনি আবার বলেন। That's perfectly okay. So let's say this variable resistor is over here. I'm going to name this as, let's say, RH, resistor variable resistor, or we could also write RV, doesn't matter. So, and then we're going to connect this thing with a long variable resistor. So a pretty long, okay, let me just draw a thin rectangle, maybe this one helps. Yay. And then we're going to connect it all the way up over here. And now we want to, we know the exact value of E1, and somehow we also know the value of R1, let's say. Actually, do we have to know these things? We don't actually have to know this. No, we don't have to know these things. We do not have to know these things. We just have a source over here made by anything, doesn't matter. And then we're going to connect an unknown source which we want to measure over here. Let's say this is a smaller source than this one, so I'm gonna give less number of cells. They're just dissimilar. You cannot find out the voltage or EMF of this cell just by counting cell number. That ratio thing is not right. They're just different batteries. This was of a bigger EMF. This is of a bit smaller EMF. Let's say we have one more internal resistance over here. And if I give a dotted box, and let's just do this, complete this rectangle, and then let's say we name it E2, and this internal resistance, let's say R2, and here comes an ammeter. We can actually use a ammeter, or we can use a galvanometer as well, anything that can be connected in series combination. And then we have the sliding contact, and this is, let's say, our jockey position. এরকম একটা সার্কিট বানানো হয়েছে। And কি হবে এই জিনিসটা আমি আবার বলছি। Let's see what's going to happen. Disregard this lower circuit first. Forget this circuit. I'm going to disconnect this altogether. How this circuit is going to run? The source EMF is E1. R1 is the internal resistance of the source, and RH is the variable resistance that is connected. And there's a very large resistance over here. Just to make the conversation easier, let me just name this resistance as the resistance left, resistance R. Or no, I can go for 1, 2. Let's say this part is resistance 1, this part is resistance 2. And let's say the length of this part is L1. And let's say the length of this part is L2. Length measurement is much too easier than measuring resistance, because length measurement only requires a meter rule or a measuring tape. Resistance measurement takes a lot of equipment. We're going to eventually use the length measurement for our benefit, for easier measurement or more reliable measurement. I'm going to show you the equation build up right now. So let's say this is the case. So now the voltage is going to divide it into 4 parts. The voltage E1 is going to get divided into 4 parts. What are those parts? The loss voltage in the internal resistance, a little bit of voltage for the variable resistance, a little bit of voltage for the R1, a little bit of voltage for the R2. এটা হবে কিনা? Is this equation all right? Respond. Is this equation all right? Hello.
স্যার হ্যাঁ ঠিক আছে এটা
All right. Now we can connect a large voltmeter over here. If you wonder why are we connecting a voltmeter over here, because we're going to take the measurement of this voltmeter reading. Let's say the voltmeter reading over here is the voltage of the voltmeter, so I'm going to write it as VV. You will not have to ever have to deal with this many number of variables, so disregard the complexity that is apparently bugging you because of so many variables. Eventually in your exam you'll have numbers, you'll directly do your math with numbers, and I'll teach you how to do that. Don't worry about that. Just to make my point, I'm using different variables. So we're connecting a voltmeter over here, which is measuring the voltage. I should not write a let me just write this okay, let me just write this as a simple voltmeter. Disregard the small v. So what will be the reading of this voltmeter? The voltmeter over here is basically measuring only VR1 plus VR2. Do you agree on this? This voltmeter reading is the total sum of these two, right?
Yes, sir.
Now comes the magic. VR1 equals to R1 divided by R1 plus R2 into V. Now you should remember that resistance is directly proportional to length. This is a full ratio of resistance, which means by the idea of proportionality, I can write L1 divided by L1 plus L2 into V. This will perfectly work. The beauty of this conversion is that this equation would require a lot of equipments to measure the resistance precisely, whereas this equation would only require a meter rule and you're done. So you'll need the voltmeter over here, and you'll need a meter rule that is connected across this wire and measure the two lengths L1 and L2, and you're basically done measuring VR1. Similarly, you could measure VR2 as well, but for the time we're only talking about VR1 because that's what we are going to work with. So measuring VR1 is very much possible. Can we agree on this? Just using a voltmeter over here, we can measure the VR1 very precisely. Do we agree on this one?
Yes, sir.
Everyone, বুঝো, question থাকলে question করো. Now I would like to show you another circuit, a different circuit, before I get back to this circuit one more time. সেটা হচ্ছে, if you have batteries connected in series in the same polarity. Same polarity means, let's say I'm going to draw multiple circuits over here. For that, I mean, let's just assume that the cell of each of these batteries have 2 volt of EMF. ideal cells. What would be the total EMF of this combination? What would be the total EMF of this combination? Count. How many volt? How many cells are here? 1, 2, 3, 4. So what should be the EMF of this combination?
8.
8 volt. Now pay very close attention and see what I'm doing. I'm going to draw 8 cells once again, but in a slightly different manner. What should be the EMF of this combination?
4.
7.
4.
4.
It should be 4. It is actually 4. Why it should be 4? Because this one is producing a total EMF of 6 volt plus over on the left, minus on the right. Whereas this cell is producing minus 2 over 2 volt, where minus on the left and plus on the 2. If you have a total combination of this whole thing, this cell is practically trying to work against this whole cell. But because this one is a much bigger EMF, this will practically dominate the effect. Hold on just a second. I just need. My bad. So in this case, this smaller cell is connected in opposite polarity of this bigger battery. So they will overpower this one's EMF and make this whole thing work as a 4 volt battery. Positive on the left, negative on the right. And whenever this circuit will work, have a look over here. If I connect this thing with a bulb over here, whenever this circuit will work, try to understand this part that I'm saying and hear me out carefully. Current is going to come out over here and flow like this. And the total EMF of this whole combination will be 4 volt. Okay. But this combination of cell will actually drain energy, and this cell will actually gain energy. Or in other words, I can say this battery will get discharged, whereas this cell is going to get recharged. And this is the exact mechanism by which rechargeable batteries work. Let me show you. Let's say a rechargeable battery in your cell phone or in any of the devices has an EMF rating of, let's say, 6 volt. Whenever you are operating your cell phone without connecting your charger, you're just using your cell phone, then this one is gonna be drained. It will run the circuits of the whole cell phone and everything. The moment you connect the charger must produce a voltage across this battery. I mean, this circuit is actually working over here. The charger unit must produce a voltage opposite to its natural current flow. So let's say that this one should be the positive end of the charger unit. This should be the negative end of the charger unit. And this must go in this way. And the delivered voltage should be somewhat bigger than 6 volts. Let's say if the delivered voltage is maybe 7 volt, then this battery will actually start charging itself for an altogether EMF of 1 volt. 6 volt would go, it will eat up this 6 volt is gonna oppose 6 volt out of the 7 volt, and the remaining 1 volt would be responsible for charging. In this process, the charging process will be pretty small because it's only 1 volt, but because the current will be very small, and because current will be very small, your I square R would also be very small, which means It's going to take a very long time to charge the battery completely, but the heat loss of the whole process will be very, very small. In most cases of our regular busy life, fast life, that might not be a very good idea. So maybe we go for the fast charging and maybe apply 15 volt over here. So now the effective EMF for the charging process should be how much? Effective EMF should be how much?
9.
That should be 9 volts, because now 6 will be cancelled out from the 15 volt. So you're now going to have a pretty large amount of current and you're going to charge up your battery really fast. But once again, because current is getting increased, the I square R loss, this is also increasing, which means your battery is going to heat up. And the moment your battery starts heating up, you start losing the quality or the life of the battery. Your battery is going to slowly start to perform less. Is gonna be its capacity in terms of joule of how much joule of energy can it store in a full charge condition, that is slowly become degraded. So whenever your phone, if you ever see your phone is getting heated up, if you don't like your phone, that's a different issue. But if you like your phone, you should stop charging immediately and find out the problem. With the appropriate rated charger, your cell phone should not heat up. And this is also the reason that it is mostly asked that people should not be using their phone while they are charging it, preferably, because whenever you're charging it, your charge giving device is operating the phone and it is simultaneously operating charging up the battery. So the amount of ampere that is pulling out through the wire is actually quite large. So if you just keep it in resting condition, it is just connected to the Wi-Fi and is connected to the cell phone network. It is only just exchanging information and doing not much processing. However, if you start playing PUBG while you are doing this, you are actually using a huge amount of processing power for your cell phone, and the amount of current drawn from your plug to your battery to your phone is actually pretty large. That can lead to some pretty destructive effects. Now, that was not my point. My point is, do you understand what is happening? Do you understand the idea of charging? If you want to charge a battery, you have to flow current reverse to its drain direction. If a battery has to drain, current has to come out of the positive end. If a battery has to be charged, current has to go into the positive end. That will reverse that charging reaction, and chemical electrical energy will be stored in chemical energy form within that battery. Does this make sense so far?
Yes, sir.
Everyone? Acha. Question থাকলে question বলো, I'll answer, no big deal. So AG situation হচ্ছে এটা situation. আচ্ছা, let's get back to this example and let's take one more example, then I'm going to get back to the original circuit. What if we connect many of these 2 volt cells in this fashion? Once again, 8 cells connected in this fashion. What will be the effective EMF of this combination?
0.
0.
0.
Precisely. So if you apply equal amount of pushing and pulling force, the resultant would be 0. Beautiful. What we are trying to do in that circuit that we are discussing right over here is that we are going to have this slider connected over here, and then we're going to connect this battery, this unknown EMF battery. E2 is the unknown. So our aim over here is to find out E2. Let me just put our aim over here. We don't know what is E2. We want to calculate that. We also don't know how much is R2. Maybe this is just a fresh cell that we just made, or maybe this is a new solar cell that we just designed, and you'd like to know its performances. So this is just a fresh equipment that you have to measure to get to understand how it is working. So what you're gonna do? You're gonna connect this thing in this manner. Now have a look, very good look, because this is the positive end of the large battery. This is also the positive end of the large battery, and this is the negative end of the large battery. And you are connecting this battery in the reverse polarity. You can see over here, this positive is also connected to the positive end, and this is connected to the negative is connected to the negative end, which means, have a look, when the current is going to come out of here, current is going to flow through this path, and current will definitely flow through this path, and there is no question about this. This path will always flow current, but there is a junction. Is it possible that the current could flow downwards? if the current has to flow through downwards, somehow it has to overpower the opposite EMF of E2, which means here comes the magic. Have a look. This is the negative end of this battery connection. So this is the positive, this is the negative end. This is the negative end. Across these 2 points, from this point, let me use red. Across these 2 points, from here to here, you are applying a fractional voltage that we named as VR1. VR1 is the actual potential that is available across this length of resistance, and you are connecting this unknown cell over here. I mean, I want you to really think and have a bit of flexibility in thinking that we can move this slider. Whatever that is left on the left is R1, and that voltage is VR1, and whatever that is left on the right is R2, and that is voltage of the R2, VR2. ঠিক আছে? Please, just a second. I have a very important call about my new house. I really have to pick it up. Okay, so we have connected this battery over here, and have a look. We are providing a voltage against this E2 cell. So if I want you guys to be blindsided, and I want you to simply observe this part of the circuit. Observe this green rectangle only. What is actually happening within this green rectangle? You have a DC source over here, positive and negative, which happens to be variable. That DC source is practically connected to E2 along with an ammeter. Is this not the same circuit? Check out.
Yes, sir.
তার মানে হচ্ছে somehow, anyhow, if I can match the voltage of this source to be exactly equal to E2, if I can somehow make the voltage of this source exactly equal to E2, within this circuit there should be no current flow, which means this ammeter should be giving us how much reading?
0 ampere.
That is precisely what we're doing. That is the thing that we're going to make null. So we're going to make this circuit like this, and we're going to slide this slider, and by trial and error we're going to find out a sweet spot such that this ammeter gives us a 0 reading, and that will tell us precisely that, have a look, when the ammeter is reading 0, there is no current flow flowing through the E2. Is E2 flowing any current? No current coming through this way, neither any current flowing through this way, which means because there is no current through this battery, that loss that could happen otherwise, I into R2, is also 0, which means you don't have any loss voltage happening for this battery. Are you having any loss voltage? There is no current.
No, sir.
The product would be 0, so there is no loss voltage. So entire EMF is now working for you, entire of the EMF. That's the whole point of making the current 0. That is the magic here. So what we're going to do, we're going to slide this left and right, and we're going to bring it at such a point so that our ammeter reading is 0, and whenever this will happen, that precise length is going to be measured, and through this set of calculation you can very easily calculate what is this value, and this thing will be the value of E2. এই পর্যন্ত কি বুঝা গেছে কিনা? বলবান, এই পর্যন্ত কি বুঝা গেছে কিনা? হ্যালো মাইক্রোফোন টেস্টিং 1 2 3 4.
স্যার শোনা যাচ্ছে। ইয়েস স্যার, বুঝে গিয়েছে।
আচ্ছা, now there will be some additional discussion for this circuit. I would like, if I draw, I'm using orange right now. If I connect another ammeter over here, let's say this is our ammeter number 1, just for the sake of discussion, is ammeter number 2. The moment when ammeter 1 will read 0, will the ammeter 2 also read 0? This is a yes or no question, and you can answer, and you are allowed to be wrong. That's the whole point of discussion.
No.
No, sir.
Why not?
স্যার কজ ওখানে তো ওই যে আরেকটা ইয়ে আছে না I don't know whether I'm correct or not.
Okay. Your response are correct. Both of your response, Ifat and Zara, your responses are correct. But I'll help you understand the reason why. Maybe you understand. That is, this ammeter reading is not supposed to be zero, because if this ammeter reading becomes zero, where would VR1 comes from? VR1 happens because current flow is happening through this long wire. This ammeter reading for this entire circuit to work will always have some value. It will always have some value, and this value can be affected by the position of this thing, by the position of this slider. This value can actually be affected by the position of this slider, but it will never be zero. If this whole thing has to work, this will be zero, because you have to understand, if at any point this value becomes zero, let's say we have a switch over here, and let's say we open this switch and this ammeter reading becomes zero, what would be the VR1 value? Also zero. Can you ever make this thing becoming zero? This ammeter reading can never be made into zero if this ammeter reading is zero. If there is no current flow through this part of the circuit, through this pathway of the circuit, there is no way that you can achieve this voltage over here, which is gonna counteract the E2, making this A1 zero. Which means if we have a ammeter in this main circuit, this will always give us some reading. This is a sort of an MCQ question that comes, and students sometimes mess it up. That's one part. This next part that I would like to discuss, that in this entire discussion, what is the purpose of this thing? Why did I connect a variable resistor over here? How could it possibly be useful? Can someone of you think? Take some time, 1 minute maybe, and think of a pragmatic purpose of that variable resistor. Is the word pragmatic appropriately used here? I don't think so. Never mind. I don't think so. বলো, আমার কোশ্চেনটা কি বুঝছো?
না স্যার
আমি যে এখানে একটা ভ্যারিয়েবল রেজিস্টার রাখছি, that variable resistor that you drew over here, why did I draw here? I mean, what is the usefulness of that variable resistor? Do we need that? And if we do, what could possibly a logical usefulness of that variable resistor?
শিওর বলতে পারছি না।
Any guess? Like, even if wrong, but any guess?
স্যার রেজিস্ট্যান্স চেঞ্জ করার জন্য লাইক ওইটার জন্য বোধহয়
Yeah, that's basically a default purpose of the variable resistor, but how does that help this circuit? আচ্ছা, আমি বুঝাচ্ছি, খেয়াল করো। বল, এই পার্টটা একটু ভালো করে খেয়াল করো, because I want you, all of you, to listen to this part with a bit more care than usual, because this is a type of descriptive question of your paper 2. So unless you understand the logical sequence properly, you might suffer. So I really want you to concentrate, and if you have any question, I'll answer your question. First, let me just state some ground information. If you have to understand that VR1 is practically a fraction of E, right? If this somehow gets bigger, obviously by some fraction this will become smaller. Isn't it supposed to be so? Let's say whenever we are working this circuit, let's say by if we choose to make this RH value slightly bigger, then VR1 will become smaller. VR1 will become smaller means what? Let's say you have this setup for your circuit, and you have matched up the A1 to be 0 at a certain value. Let's say this whole wire is exactly 1 meter, and let's say this location over here is, let's say, 67 centimeter. I was getting about 2/3, so 67 centimeter. Now, if I increase this value slightly, then the actual voltage available across this part of the wire will reduce, right?
Yes, sir.
And when that will happen, E2 will become the bigger source. So try to visualize over in this circuit. If this one becomes slightly small and this one becomes the bigger one, then this one will drain. So then the current is going to start flowing through this way. So now my question, if you now want to make this ammeter reading 0 once again, if you want to achieve this right now, in which direction should you move this slider, left or right?
Right.
Right. Hear me out. I'm saying the question once again for those who couldn't catch it. In this position where we increase the resistance of this variable resistor, as a result, the VR1 value got somewhat reduced and ammeter reading is no longer 0. If we now once again want to make the ammeter reading 0, in which direction should we move the slider? Should we move it to the left or should we move to the right? তোমরা সবাই কি ক্লাস করতেছো?
স্যার রাইটে হবে।
Acha, we should move it to the right because now the VR1 got somewhat smaller than E2. E2 has a fixed value. E2 is a default value of the cell or the battery. So if we want to now match up that value, we have to now use a longer length. So we have to move it to the right and vice versa. So this is the advantage of the RH value of this variable resistor, is that we can take multiple readings of a single battery and compare those values to get an average value of this thing. If you don't have this, let's say if you did not have this thing, have the variable resistor, you would only get one spot over here, and you have to do the one set of calculation. That's basically done. There is no way you would have option to take multiple readings to get more reliability. You know that repeat and average is one of the very important aspect of any experiment. If you want to get reliable data, you should always do repeat and average. This component over here allows us to do that repeat and average. এইটুকু কি বুঝা গেছে?
স্যার রিপিট এন্ড অ্যাভারেজ মানে বলছে যে মানে মাল্টিপল অফ রিডিংস নিতে পারবো ডিফারেন্ট পয়েন্টস এর, ওইটাই তো, তাই না?
এইটাই এক্স্যাক্টলি আমাদের এল এর ডিফারেন্ট ভ্যালু আসবে, এবং এল এর ভ্যালু যখন চেঞ্জ হবে তখন তোমার এই ভ্যালু তো চেঞ্জ হবে, কারণ whenever we change this one will also undergo change, and your L1 value will also change. So you're gonna use this whole set of calculation once again and calculate the value of E2. And you can have let's say if you do six different measurement, and from the different measurement you get 6 different values of E2, and then you average all of these up and you publish that as your result. That is a more reliable way of doing the experiment. এটা কি বুঝা গেছে কিনা?
ইয়েস স্যার।
আচ্ছা, আরেকটা অ্যাডভান্টেজ আছে। আরেকটা অ্যাডভান্টেজ হচ্ছে, এই অ্যাডভান্টেজ সবাই বুঝছো? বাকি সবাই যে রিপিট এন্ড এভারেজ করার জন্য আমাদের ওই ভ্যারিয়েবল রেজিস্টারটা ইম্পর্টেন্ট, এটা কি বুঝছো সবাই? এভরিওয়ান?
জি স্যার।
আচ্ছা, I have actually three or maximum 4 of the persons actually making some response. Can I have a yes or no from everyone? Like there are 9 people in the group, so apart from me there are 8 students. I'd like to see 6 yes or no's. Oh, sorry, 8 yes or no's.
কি মেসেজ করে দিব?
না এই যে আমাদের এই যে উজমা লিখছে, হ্যাঁ চ্যাটে লিখো 2 3 4 5 what 1 2 3 4 5. Yes, we have 5. Where did the other 3 people go? Oh yeah, Tausif wrote yes as well. 6. We have 2 more people left.
স্যার বাট 7 জন তো রিপ্লাই করছে।
7 জন reply করছে? 1 2 3 4 5 6 7. Yeah, and the participants in the participant list I have 9 people, which means there should be 8 replies, right? Ahnaf Islam is missing from the reply list. Okay, maybe we'll sort this out later because we are running out of time. So this is one of the advantage. The other advantage of having a variable resistor over here is this. Let's say you have a setup like this. You work in a laboratory of a research farm, and your day job is to measure the EMF of different
Sir, did
cells.
you call me?
Sorry.
Never mind. Continue.
আচ্ছা আচ্ছা Anav, you're here. Okay, fine, good. বুঝে গেছে কি ওটা যেটা কোশ্চেন করছিলাম বুঝে গেছে?
Yes, sir.
So the second advantage is that let's say you work in a research farm where they produce different cells, and your day job is to measure the EMF of different cells every day. So some of the cells might have a pretty high EMF, some of the cells might have a pretty small EMF. You don't know, you don't have any clue what EMF that cell holds. Now here's the deal. One thing you have to always understand, for this whole circuit to work, E1 must be bigger than E2. Your main cell must be bigger than E2 because you are actually using a fraction of E1 to become equal to E2. So you have to have your E1 bigger than E2. That goes without saying. But let's say on a certain day you are let's say the value of E1 is, let's say, 12 volt. And on a certain day, let's say on day 1, you are measuring an unknown cell of E2 of, let's say, 8.3 volt. And on second day of your job or of a week, or let's say you are having another cell which has a E2 value of, let's say, 1.9 volt. Now have a look. This is a really small voltage compared to this one, right? Compared to
Yes,
this value,
sir.
this is a very small value. So which means if you use the same value of RH that you used in this experiment over here, you'll always get really small values of lengths. So all of your 6 data or 10 data will clamp up for very small. So you're not actually using all of your available space on the wire. Isn't that going to happen? কথাটা বুঝো। If we do this, all of our values will happen for a very small length of wire. So we'll not be using the whole length. So to get a more reliable result, we should prefer to design our experiment in such a way so that we can have those sliding positions in a quite spread pattern, so that we can use all the available space of the information. Oh, acha, Anna, it's all right. It's all right. My bad. So এই জিনিসটা হচ্ছে important. So because we want to use the entire space, whenever you are working with a small voltage, you would want this variable source also to provide you a small voltage. And what is an effective way to make this source a smaller voltage? By making the rheostat eat up a bigger fraction, so that your VR1 becomes significantly smaller, so that your slider can be pulled more to the right. Now I want you guys to see, have a look at things. Let's say this E1 has a value of 12 volt. Think about it. Let's say this V1 eats up 1 volt. Just for the sake of simplicity, it should never eat 1 volt. And then let's say the VR1, and let's say if I can adjust the value of this thing in such a way that the total sum of this whole thing is, let's say, 2.5 volt. And in that case, what should be the value of this one? Subtraction করো তো একটু। 12 minus 1 minus 2.5 কত হয়? 9.5, 8.5, 8.5 না?
Yes, sir.
8.5. So if you adjust the VRH to be 8.5, then the total voltage available across the entirety of this long resistance wire would be 2.5 volt. So measuring a smaller voltage of what? Of 1.9 volt, you can have multiple connection points on your resistance wire, making your experiment procedure more reliable. Contrary to or in contrast with, let's say if you keep the same setup and you let's say in other sense, let's say if I use a dark blue over here, let's say on day 1 you measure the EMF which was 8.3 volt. To measure 8.3 volt, you need this one to be 8.3 volt. Let's say the total sum of these two were in that day was 10 volt. If this was 10 volt, then the VRH was only 1 volt. So this is 1, and this is 10 volt. which means now 2.5 or 1.9 volt would be only covered in a fraction of about 19% of this whole thing. ঠিক না? If you do not change the setup to this setup on day number 2, if you use the settings from the first day, you're going to end up with a very small number. So that is something that we don't want to happen. We want the total voltage available across the entire wire should be slightly smaller than the E2 value, but we don't know what is the E2 value, but we want that to be slightly smaller, not too much smaller, not too much bigger, within close proximity. But obviously VR1 plus VR2 should be bigger than the VR1, but we don't want that gap to be really large. Do I make sense so far? এই পার্টটা বুঝছো কিনা দেখো, না বুঝলে আমাকে জিজ্ঞেস করো। বলবান বুঝা গেছে কি সেকেন্ড অ্যাডভান্টেজটা?
স্যার আমি ঠিক করে বুঝিনি।
বলতেছি জিনিসটা হচ্ছে যে মনে করো তোমার কাছে একটা এত বড় একটা কেক আছে, ধর এটাকে আমি বললাম যে এটাকে 4 পিস করো, তুমি এখন ক্রিকেট খেলার স্টাম্প দিয়ে এটাকে ইজিলি 4 পিস করতে পারবে, বিকজ দিস ইজ এ বিগ থিং। But if I give you a small cake piece and ask you to make this into 4 equal pieces, you're gonna need a thin string or a wire or a sharp knife so that you could make it into 4 equal pieces, right?
Yes sir.
Measuring a large voltage, you require a large voltage across this thing. Measuring a small voltage, you would require a smaller voltage across this thing, like that. It has to be scalable. Not scalable is not that word here either. It has to be, I mean, within close value to each other to get a more reliable number, so that we do not get stuck with a very small fraction of the wire. We can get all of our individual readings spread all over the wire position.
আচ্ছা স্যার।
ঠিক আছে? All right kids, I superbly appreciate your patience. আমি এখন রাখতেছি কারণ হচ্ছে আমার O level এর একটা ক্লাস আছে, it's exactly 7:30. I'm really happy that we finish perfectly on time. And হচ্ছে কালকে তোমাদের সাথে আমার 9:30 ক্লাস আছে, I'll definitely do that class. And please একটু তোমরা পারলে দুপুরে একটু ঘুমায়ো যাতে করে ওই ক্লাসটাতে জেগে থাকতে পারো। That's all I'm asking. আর হচ্ছে আমি লেকচার এই যে আজকে আমার 9:30 ক্লাস শেষ করে আপলোড করে দিব। যদি তোমাকে রিভিশন করতে চাও বা whatever, if you want to see anything else, look it up from the YouTube. I'll upload it tonight for sure.
স্যার
বলো।
স্যার আমি স্যাটারডে দিন অ্যাবসেন্টও থাকতে পারি, কজ আমার ডক্টরের কাছে যেতে হবে, তো তো যদি অ্যাবসেন্ট থাকি তাহলে ভাববেন যে ওটার জন্য আসিনি আর কি।
আচ্ছা সমস্যা নেই, it's okay. Health is first anyway. You have to live to be to put your education into purpose. Okay, Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz.